So in this video, we talk about multiple input, multiple output systems interacting with the stochastic process. So if you have a system which has multiple random processes as input and multiple random processes as output, I put all the inputs in a vector. I call it input vector random process and output vector random process, and multiple input, multiple output system. So the mean of the input is defined as mean of these random vector, which is also a function of time. Mean of the output is also similar. So it's kind of like the cross correlation of the input with itself is equal to, because these are column vector, and if they are complex, I put a Hermitian. Remember that Hermitian of a vector is equal to that the same vector transposed and also complex conjugated. So this is a column vector, this becomes a row vector. When you multiply them, it becomes a matrix. Once it becomes a matrix, n by n, so you calculate expected value of all entries, and this gives you auto correlation matrix. Okay, or you can have the cross correlation matrix between inputs. So this is a column vector, this is a row vector, and becomes n by m, the cross correlation matrix of input and output. Or you could put y first and x as second. Then in that case you have a vector of size m and a row vector size of n. Remember that we put transpose and conjugate on the second one, and the first one is always a column, second one is a row vector. So this makes it a matrix. Obviously r x y of t1 and t2 is equal to r y x of t2 and t1 complex conjugate and transpose, which is Hermitian. So is these two matrices, they are Hermitian of each other. But the first one you can see that r x of t1 and t2 is equal to r x of t2 and t1 Hermitian as well. So this is always true. And ry1 of t1 and t2 also is defined like that. So this is as example, you could cascade these two random vector processes, and then so the size of these z, because the first one has n entries and the second one has m entries, so these will become n plus m times 1. And then you could see that RZZ becomes a matrix like that. And the first component is this one, and the second one is this one. This is the third one, and this is the last one. So the Mimo linear time invariant systems is the case that you have a system which has n inputs and an output. So they are characterized by a impulse response matrix. So the y of t, which is a vector random process, is equal to this h of t as a matrix convolved with x of t. So remember that you cannot change the order of this one and this one. So this is written as a convolution of this matrix h of t minus alpha. Alpha is a dummy variable. X of t will become x of alpha, d alpha, and then alpha varies from minus infinity to plus infinity. Remember that you multiply this matrix by this vector, and then you will get another vector, and then you integrate with respect to each entry of that vector. So matrix multiplied by vector becomes a vector. Entries of the resulting vector are integrated over these dummy variable alpha from minus infinity to plus infinity, and it gives you a signal. So this Mimo LTI system has a unit impulse response matrix H of t. So the entries of this matrix, the PQ entries of that is the unit impulse response, because you have multiple inputs and then you have multiple outputs. So these H, P, Q, T, the entry PQ of these. So if I write this one, that means that the Qth input, so let's say this is Qth input. So this is number 1. This is number 1, 2, etc. So you take the Qth input, so you have a random process at the input, and then you consider the Pth output, you get another random process. So if you give a delta t at the Qth input, you observe some responses. So the Pth output will be H PQ. Okay, so you put all these unit impulse responses in a matrix and call it unit impulse response matrix. So in that case, you can write this relationship. Remember that this guy is a matrix H and this is a vector. So entries of x of t are in here, and entries of H are the impulse responses are here. And then you get, this is going to be after the integration, you get the entries of y of t. So now, so you can write it as a convolution. Now, this integral convolution, you can multiply this one. You can replace t by t2. And then you can calculate xt1 times y Hermitian times t2. So I substitute this t by t2, this one by t2, this one by t2, and then I have to put this Hermitian over it. So and then I multiply it by xt1. So and then I could put xt1 inside the integral. I get this one. Now I could apply expected value, expected operator on both sides. So if I do that, here I get r, x, y at time t1 and t2. And then expected value can go inside the integration. I get integral over dummy variable alpha from minus infinity to plus infinity. Expected value of these will become r, x, x at time t1 and t2 minus alpha. And then I will get h Hermitian of alpha, d alpha. Now this equation, what it says is that r x, y of t1 and t2 is equal to r x, x of t1 and t2 convolved with h Hermitian of t2. Remember that in this convolution, t1 is fixed. So this relationship is important. I could write a similar result instead of xt1 yt2. I could write it in like yt2 xt1 Hermitian and so on, or I could write it yt1 yt2 Hermitian. So you could get all these results, and then you could get also this one, and then these will become equal. But remember that in this convolution, I could because when I don't deal with multiple input, multiple output, I could change the order of the convolution. But here, because I'm dealing with vectors and matrices, the order is important, so I cannot change the order of these two guys or these two guys. So here I fix t1, I put this one here, and then here one. So this is going to be equal to ht1 convolve ht2 with rxx of t1 and t2, but another convolution with h of t2 Hermitian. So I emphasize on two things. The order cannot be changed. You have a Hermitian. A Hermitian is transpose and conjugate. The order of these convolution cannot be changed. When you do this convolution, this T1 is fixed. When you do this convolution, the first convolution, T2 is fixed. So, so this is the final result. So the autocorrelation of the output can be written in terms of the unit impulse response matrix, convolution, T1, T2. Remember, in the second convolution, T1 is fixed. In the first convolution, T2 is fixed. We could have one example for that. In this example, my multiple inputs has only one entry, so it's a single input, and then I have two outputs. So the first output is just convolution of the input with the arbitrary impulse response, and the second output I wanted to have x of t itself. Okay, so here the impulse response here is just delta t, because delta t, whatever input you give it to it, it will give you some output. So my y of t has two entries, x of t convolved with h of t and x of t convolved with delta t. So I could say that this is convolution of x of t convolved with a matrix of h of t and delta t. So this is my unit impulse response matrix, which is a column vector. So I could use the expressions in the previous slide. The RYY of T1, T2 is the convolution of h of T1, RXX of T1, T2, and convolution with h of T2 Hermitian. Remember that this convolution T1 is constant, fixed, and in the first convolution is T2 is fixed. So if you write this convolution, multiply them, you get 4 terms, because this guy is a scalar, and then you can simplify.